All right. Then it just turned 10 o'clock. So I would say we get started. Also, thanks to all the people who already joined. Yeah, I see that the numbers are still growing. So people last minute logging in are still coming. Welcome everybody to today's webinar from HIOKI, battery testing in the production line, do's and don'ts, where we really want to go about tips and things to do and how to better achieve better testing results in the battery production line. Today with me and the main presenter is 𝗖𝗵𝗲𝗀𝗀, head of our product management department. Okay. So very quickly, I just want to go over the structure of the webinar, just some housekeeping, basically. We take about 30 to 45 minutes. We assume our participants are basically muted, so there will be no commenting. However, you are invited to ask questions. For this, in your taskbar down there, you find a Q&A button. It may be named differently depending on your language. Please put only your questions in there, because the chat function is disabled. Only the Q&A function for your questions to a certain slides during the presentation or after the presentation. Please type to us, we will answer them. Remaining questions will be answered by email after the webinar. Also, the webinar is recorded. So first of all, just for you to know, for all the questions that we handle and the naming that we say it's recorded, but also you will get the link to the recording in the materials after the webinar. Okay, so I just want to take the opportunity quickly go introduce HIOKI for those of you who are not so familiar with us. So HIOKI is a manufacturer of electrical test and measurement equipment, and started in 1935 already with the manufacturing of electrical indicating meters. So we really are from the trade, from this. This was our business right from the beginning of the company. By today, HIOKI has around 1,000 employees worldwide and 250 million euros turnover. Important things for us to mention is that HIOKI is very much an engineer-driven company, and this really is, you can see in the products that we are bringing out, and also all of our products are made in Japan. So this is one of our trademarks really that we show. This is what we're proud of, also the great quality that we are bringing to the market. And since 2017, we are here in Europe, so in a subsidiary. Could you go back?
Yeah.
All right. So our portfolio basically splits up in three big areas: automatic test equipment. So we have boarded and populated and bareboard testing, but also FMI on the right you see, like field measuring instruments, handheld instruments. But we focus mainly also on the center part professional measuring instruments, also which ranges from LCR meters, impedance analyzers. We're very strong at current sensors as well, but also power meters, power analyzers. And today, what is you see in bold here, what we want to talk about affects you more is the area of battery testing with all the different instruments that we need here. So we go to the next slide. You can see, so what makes us so special and how we could build up this expertise in battery testing. Our first battery testing instrument was actually launched in 1986, which was only a year after Asahi Kasei came up with the first production-ready lithium-ion battery. So right from the first moment of lithium-ion battery production, we were there with our first solution for testing. And of course, this has been sped up after like the e-mobility and new technologies picking up speed also in the 2000s. Also the development and innovation of new testing methods and instruments have been sped up also with HIOKI. And since then, we're working very closely with battery manufacturers on the one side, but also with car manufacturers who are into new mobility technologies. So this is where we have a lot of experience with the testing procedures, but also with the how it is really used in the field. And based on this, I would like to hand over to 𝗖𝗵𝗲𝗀𝗀, who will, based on this experience, share some of these tips, do's and don'ts for the topic of today.
Okay, Oliver, thank you very much for the introduction. And before we dive into the technical part of the webinar, I'd like to explain why we decided to organize it in the first place. At our office in Eschborn, Germany, our customer support team frequently gets questions related to battery testing in the production line. Most of them are related to poor reproducibility of ACIR measurement. With the experience within HIOKI supporting our customers in China, Korea, Japan, and Europe, we know what can go wrong with ACIR measurements and can give valuable advice on how to achieve accurate and reproducible test results in the production line. Let's go through the content of the webinar to give you an idea what we are going to cover. We will start with a short explanation of the principle of ACIR measurement, followed by the measurement examples what can go wrong, what the reasons is that it goes wrong, and what we can do to solve the issue. After that, we will provide suggestions for troubleshooting in the production line. We will close the webinar with a summary and a Q&A session. Internal resistance of the lithium-ion battery is a reliable indicator for its quality. ACIR measurement is therefore a popular test in the production line. Let's dive into the principle of that measurement. In principle, it's quite simple. A stable AC current is connected to the battery, flowing in this direction. At the same time, we are going to measure the voltage over the battery. With these two parameters, we can, using the Ohm's law, calculate the internal resistance of the battery. The measurement is done in accordance with the IEC 61960-3 standard. This standard describes how to do the measurement. The standard specifies that the frequency of the AC current signal must be 1 kiloohm. This is important because the internal resistance of the frequency depends on the frequency. So it's frequency dependent. And when you want to compare tests which are performed, for instance, in China with a test being performed in Europe, then you need to make sure that you do the test at the same frequency. As the resistance of a lithium-ion battery is just a few milliohms, or even more, or even less sometimes, it is necessary to use a 4-wire measuring principle. This method eliminates the influence of the connection resistance. The connection resistance consists of the wire resistance and the probing resistance. The connection resistance is much higher than the internal resistance of the battery, and therefore it needs to be cancelled out to have an accurate measurement. The 4-wire method works like this. You have 4 contacts, and these contacts, they are the source high, source low, sense high, and sense low. The source circuit is used to contact the test current to the battery. So the test current is flowing in this circuit through the battery. The other 2 connections, the sense connections, are connected by 2 different wires. As the input resistance of the voltmeter is very high, there is virtually no current flowing through these wires for the sensing, which means there is no voltage drop over the wires and the contact resistance. And that makes it possible to accurately measure the voltage over the battery. And then, once again, with Ohm's law, we can calculate the resistance, internal resistance of the battery. Now we know the basics of ACIR. We are going to look what can happen when you use sensitive instruments like the battery testers in a production line. and what you should do to ensure reliable and reproducible measurements. The first thing that we are going to look at is correct wiring. Poor test results are basically related to three main categories: the wiring between the battery and the battery tester. And due to the use of motor inverter drives in the production line, electromagnetic interference is a common issue. Also, the effect of eddy current and the use of multiple testers at the same location can influence the accuracy of the measurement. Probing is another area where errors may occur. This can be because of poor probe pins, but it can also be because of the positioning of the pins on the battery itself. We're going to look into that as well. The third category, which is basically the introduction of a multiplexer in the production line, is also an issue of many questions that we get. We're going to look into that subject as well, and going to give you some advice to have accurate measurement when you are using a multiplexer in the production line. So we start with the wiring first. What influences can the wiring have? The first thing that we have to consider is that electromagnetic inductance can influence the test results. How does that work? Well, the battery tester is using a measurement current, and this current can be quite high, especially when you are measuring at low internal resistance. For instance, the battery testers that we have use for the low resistance range 1 amp. And this AC current causes a magnetic flux, and that magnetic flux can be picked up by the sense wire. So it will induce a voltage in the sense wires that will interfere with the measurement signal if not the right precautions have been taken. Besides that, there is also a magnetic flux in the production line itself due to magnetic or electromagnetic interference from, for instance, the inverter drives, solenoids, or other measuring instruments. And this can also induce a voltage on the sense wire, and that's what you have to overcome. So a lot of these problems can be eliminated by twisting the wires. And why and how does that work? I will show you in these two graphs. Here on the top, you see the source wires. So the measurement current is flowing through the blue wire, the twisted blue wire, from left to right to the battery, and returns in the yellow wire from right to left. And because you twist them, and if you twist them very close, the cables are very near to each other, you can see that the current is flowing in opposite directions. And because of that, the currents are basically compensating for each other for the electrical flux, which means that there is no creation of electromagnetic flux when you twist the wires. On the sense side, it's working in a similar way, but then, of course, your starting point is the inductance, the flux, the mechanical flux, electromechanical flux, and that's the blue error. And the blue the flux will create a voltage in the wire, but as you can see, for each part of the wiring, the direction of the voltage is opposite. So you can see here in this part of the twisted wire, it's going to the left. The next one is going to the right. The next one is going to the left again. And the sum of all these voltages is 0. And therefore you have a good immunity against electromagnetic noise by twisting the wires. maybe this is all a little bit much, but we're going to look into a few tests, and with that we can explain the situation. For these tests, we are using, for practical reasons, not a battery, but a small and accurate measurement resistant. And as you can see on this slide, we have done this with this resistor of 1 milliohm. And in the first test, we connected the resistance just with wires where there is no twisting. In the yellow wire, which is the source high wire, the AC current is flowing, causing the electromagnetic flux, which is picked up by the sense wire, the sense plus wire, the red one, and then induces the voltage. The same thing is happening on the other side. And therefore, you have a whole area where the magnetic flux is picked up by the sense wires and cause and induce a voltage in the sense wires, making the measurement inaccurate. In this situation, you can see that the measurement error is 11%. After we have twisted the wires on this for the sense and for the sense and for the source wires, you can see that the accuracy has improved dramatically, showing that the interference from external signals and the induction, the electromagnetic induction, have been cancelled out. Another influence on the measurement is the eddy current. Eddy current is related to electromagnetic induction, and you can see here, once again, the measurement current is causing a magnetic flux, and this magnetic flux will cause an eddy current in metal plates which are nearby the source current. As a result of that eddy current, there will be an additional magnetic flux, which on its own will also be picked up by the source or the sense wire and interfere with the measured voltage over the battery. So it's related, but it's caused by metal plates which are very nearby the source wire. To show the effect of eddy current, we are going to the next slide, and you can see what will happen. So basically, we have repeated the first test with a situation where we don't twist the wires, and then you can see that there is a measurement error of already 10%. But if we're going to put a metal plate nearby these wires, you can see that the error is increasing a lot to 45%, meaning that it's really a very big impact of the eddy current. So what can we do about it? Well, once again, the solution is twisting the wires. So once again, twisting the sense wires and twisting the source wires. As you can see then, without the metal plate, there is a measurement error of 0.13%. But even when we put the metal plate nearby the wires, the measurement result is not influenced. So twisting the wires is a very efficient way of cancelling out the eddy current, the effects of eddy current. Another problem that can arise is when you have multiple instruments in the same location in your production line. As you can see here on the two left pictures, if you have switched on only one instrument, the effect of or the results are quite okay. The error is minor, and also here, even the error is 0. But if you switch both of them on, then you can see that the error is occurring. And that means that because of the test current which is flowing in for instance, this right instrument, that will interfere with the sense wires of the other instrument, creating another or induce another voltage on the sense wire, and therefore creating unstable and inaccurate measurement results. Maybe it's getting a little bit boring, but this can be solved once again by twisting the wires. Here you see on the right-hand side that when the wires are twisted, that we have a very accurate measurement result. And by now you might conclude that twisting the wires solves all the electromagnetic influences and eddy current issues. But there is more to be told. There is also another wiring method called the 4-terminal pair wiring method. We are using this method specifically for one battery tester, and that's the BT4560. This BT4560 battery tester can measure the internal resistance of a battery at 1 kilohertz, but is also able to measure at lower frequencies. For instance, about 1 hertz. And when you measure at 1 hertz, you can identify the electrode and the reaction resistance of the battery. And therefore, it's also quite popular in the production lines of high-end battery cells. What's the main difference between the normal 4-wire measurement and the 4-terminal pair wiring method? Well, the main thing that is different is that we use coaxial cable instead of twisting wires. The principle is like this. So you have your same AC source, and the AC source first is going through the core wire of the coaxial cable, then flows through the battery, returns to the instrument with the other through the other core of the coaxial cable, but then it returns again, but through the shielding of the coaxial cable. As you can see here, because of the opposite directions of the current, also the magnetic flux resulting from the measurement current is cancelled out here. Also, nearby the battery, you have to have a return cable to connect the signal, the current signal from this coaxial cable to the core of, or to the shielding of this coaxial cable. And then the current is flowing back into the battery tester, also for this cable having an opposite current, which cancels out the electromagnetic field. So this is a very effective way. And why do we use this for this particular battery meter? It is because the test current of this BT4560 at the low range, the 3 milliohm range, is even higher than 1 amp. It's 1.5 amp. And if you then don't take very good measures to control your magnetic flux, you will have influence of the measurement. So this method is very efficient for cancelling out electromagnetic induction. But also because of the coaxial cables, and we can connect the coaxial cables, the shielding of the coaxial cables for the sense wires to Earth, it is also giving a very good protection against electromagnetic interference from all kind of other signals in the production line. So it is very effective for eliminating EMI. There is, however, also a disadvantage for this wiring method. And that is that if you look here, you can see that the source current is traveling first through the battery and then back to the battery tester, and then once again goes through the shielding, through this return cable, back to the shielding of the other coaxial cable and back to the measuring instrument. this is a distance which is twice as long as with the standard twisting solution. So that's the standard 4-wire measurement method. Meaning that when you use the BT4560 in a production line, you need to take care that the length of the cable between the battery and the battery tester is not long because of the long circuitry of the source signal. So we've looked at wiring, and now we're going to look at what can cause issues when you have probing of your battery. But first, I'm going to explain a little bit about the overall connection resistance. Like I mentioned, there is a relationship between the total resistance of the connection wires and the internal resistance of the battery. This one is very small, and compared to that one, the wiring resistance is quite high. In this graph on the right-hand side, you can see that when the connection resistance for instance, R3, which is the sense low wire, is increasing. So the length, basically, the resistance is increasing when the length of the cable is increasing or the wire is increasing, that it has an influence on the measurement error. In other words, what this graph shows is that when you want to have an accurate measurement, you should try to reduce the length of your measurement cable as much as possible. Now, let's move on to probes. What kind of probe do you need to use to connect to the battery? There's a wide range of probes available on the market, but we always advise to use a single contact probe, like for instance a needle probe. Reason for this is that the reproducibility of that measurement with a needle probe is much better than when you use another probe, a multi-contact probe, like for instance the crown probe. You can see an example here. Then the measurement result is a lot poorer. Our engineers have done some tests. So they did 20 measurements using a single contact probe, and then you can see that the reproducibility of the measurement is quite good. The difference is only plus minus 2 microohm. And you can see here, for instance, the blue line, which is the resistance, it has very, very little variation. It is almost as flat as the Netherlands. But if you look at the connection with the multi-connection probe, you can see that, yeah, it's all over the place. And there is a reproducibility error of almost 30 microohm. And when you consider that your battery has an internal resistance of less than 1 microohm, this is something that you have to consider. So, in general, conclusion of this is that you should use a single contact probe to get good repeatable measurements. The positioning of the probes in the battery, on the battery, is another factor that influences the reproducibility of the measurement. To decide what is best, we first have to understand what happens when you connect the source current to the battery. If you connect the source current to the battery, the result will be that there is a potential gradient, basically a voltage curve, which will exist from the moment the current is flowing through the battery. And as you can see here, there is at the point where you probe your high probe, an immediate steep drop of the voltage. After that, the curve is flattening off, and when it's getting nearby the source low probe again, the curve is getting steeper again. So This is what happens when you are connecting your source signal to the battery. So it's very often considered the best results for achieving a good measurement, internal resistance measurement, is that the probes for the source and the sense should be very close to each other. However, if you look at this, you can see that when you put them very closely together, you're going to measure here at the very steep part of your potential gradient slope. In other words, if you want to do repeatable measurements and have a good reproducibility of your measurement, it is very difficult if you do that on this very steep part of the slope. The slightest changes in positioning will have an impact on the voltage that you measure, and therefore on the repeatability and the reproducibility of your measurement. So small tolerances in position of the sense probe will have a big impact on the measurement voltage, because we are measuring in the steep part of the curve, resulting in low reproducibility of the measurement. If we position the sense probe a little bit further away from the source probe, we are going to measure at a less steep part of the potential gradient curve. And as a result of that, the tolerances in the probing are becoming less important. If there is a small tolerance in the positioning of the sense probe, the measurement result, the voltage will not change that much, and therefore you will get a better reproducibility of the measurement. At the production line, reproducibility is normally considered more important than absolute accuracy, because you want to be able to compare the test results from day 1 with the ones from day 3 or from day 10. Positioning of the source and sense probes a little bit further apart will help you to achieve a better reproducibility of your measurement. Then we're going to look into the use of multiplexers in the production line. Whether or not to use a multiplexer for ACIR measurement in the production line is another consideration. Using a multiplexer will reduce the number of battery testers and can therefore reduce the initial investment. Further, the use of multiplexers increase the flexibility of the battery test line. When you want to increase the number of batteries, then it's very simple. You just add another multiplexer card and you can have more battery tested without having to increase the number of battery testers. On the other hand, using a multiplexer will result in a longer testing time. So you will have multiple measurements at one location after each other. And when you have multiple instruments in parallel, then the measurement can be done simultaneously. So it will take you a little bit more time to do the measurement. And one of the other important disadvantages of using a multiplexer in the production line is the zero adjustment. That is a lot more complicated when you use a multiplexer than when you do a direct measurement. I'm not going into that subject. It's a very complicated subject, and maybe it would need a webinar on its own to explain about this zero adjustment in the production line. But let's move on. So another thing that you need to consider is that when you start using a multiplexer in the production line, you have to make sure that it is designed for making ACIR measurements. We have seen in the previous slides that there is a lot of influence from electromagnetic induction or electromagnetic interference on the measurement result. And you have to make sure that the design of your printed circuit board is done in a way that you have a good separation of your source signal from your send signal. Also, the size of the send signal should be minimized as much as possible, because there it is where you pick up your signals for the electromagnetic interference. So the smaller the part of this circuitry is, the smaller the circuitry is, the less chance you have that you pick up the noise. And further, the design of the printed circuit board should guarantee that the measurement current is flowing in opposite directions very nearby each other. Because we have seen when we twist the wires, we can compensate for the generation of magnetic flux. And therefore, also a multiplexer, which is used for ACIR measurement, should have the patterns in the printed circuit board for the high current, for the source high and source low current very near to each other. We're going to look into some tests that have been done with one of our switch modules. You can see here on the graph, here is the multiplexer that we often combine with the ACIR measurement. And our engineers have done tests to see what the result is when you introduce a multiplexer in the system. There are a lot of information on this slide, so I think it's better to introduce them very briefly. Here you see a brown horizontal line, and that brown is basically the reference of all the measurements. It is the measurement that has been done on the battery when we connect it without a multiplexer, so a direct connection. So this is basically the reference value of the measurement. Further, we see here two gray lines, horizontal lines. These lines basically, this is the accuracy range for the battery tester itself. So if the results are within these two values, then the measurement result is considered to be accurate and according to the specifications of the battery tester. The two horizontal red lines, they represent the combined accuracy of the battery tester and the switch. And if your results is within these two these two lines, then you can consider that the combined measurement accuracy has been met. Here you see a dotted line, a dotted green line, which is very flat. And this green line represents a measurement that has been done with the battery tester and the switch. And the switch is connected in slot 12. So here, completely on the right side of the battery or the switch mainframe. After that, the switch is connecting to the same battery on all the 11 channels. So one input card has the capability to do 11 4-wire measurements, and therefore we can connect basically 11 batteries to one of the input cards. But for this test, it was all measured at the same battery. As you can see here, it's once again a very straight and flat line, meaning that it doesn't make any difference what kind of channel you use in your multiplexer, you will get a similar result. The same test has been done, but not in slot 12, but in slot 1. But yeah, unfortunately, I cannot show you that result because it's underneath the green one. So showing that it is exactly the same result as when we had the switch module in the right, in channel 12. This basically shows that it doesn't make any difference where you put your multiplexer card. Your result will be have a good reproducibility of your measurement. If you look at the other one, though, this is a combination of our battery tester in combination with a multiplexer which was not properly designed for ACIR measurement. And then you can immediately see there is a wide spread of measuring results, meaning your reproducibility of your measurement is not okay. If you have this kind of situation, there's nothing that can help you, because it's very unpredictable what your measurement result is. So make sure that you are going to use a multiplexer that is suitable for ACIR measurement, like, for instance, our SW1002. So we've spoken about a lot of things that can happen, but all was basically theoretical. So let's now go to the guidelines for the troubleshooting, which is more the practical side. There are many factors that can cause degradation of the measurement accuracy in the production line, like temperature fluctuations, humidity changes, EMI, etc. It can be a struggle to identify the cause of the problem with so many different variables. This is why we always advise to go step by step. Change only one of the possible causes, like, for instance, the routing of the measurement wires, and check if that gives an improvement. If that isn't the case, then maybe fix another of the items, like, for instance, is there any metal plate nearby the wiring? Remove the metal plate and see if that has an impact, an improvement on the repeatability of your measurement. This you can do for many of the causes that are possibly the reason for a bad reproducibility. So the general rule is change one thing, do a test, and then do another test when you have done another change. So step by step, we'll identify the reason why you have inconsistent measurements. Therefore, we have now an example. This is showing you the reproducibility of a measurement in a production line. Well, you can see that there is a wide spread of the result. What you expect is roughly 1 milliohm, but there's almost a spread of 0.2 milliohm, which is not acceptable, of course. What you can do in that kind of situation is to perform two different tests. To identify the cause of the problem, you're first going to do a test where you connect the battery and perform 10 measurements without disconnecting the battery. If in that case your measurement result is more repeatable, then you know that the cause of the problem is with the connecting to the battery. If you then perform a second test, and then the second test is that you're going to disconnect the battery between each of the 10 measurements, and you will see that once again there is a poor reproducibility of your measurement, then you absolutely are sure that making contact to your battery is the issue. And when you know that making contact to your battery is the issue, you can focus on looking what the problem might be. It could be that your probe pins need to be replaced because they have worn, but it can also be that they are not fixed in a proper way and that there is a little tolerance when you are probing with your battery. Or it could even be that the battery is not firmly fixed before you're going to do the measurements. And if that moves, the battery moves slightly, that will also give you a poor reproducibility of the measurement. But with this test, you narrow down the possibilities of problems. And that's what basically the message is that we want to send out. So this closes basically all the technical information that we wanted to share. And we're going to look in a short summary what has been told. First, of course, wiring. Main message is keep your wiring between the battery tester and the battery as short as possible. Always twist the source high and source low wires and the sense high and sense low wires. And keep your wiring far away from metal parts and plates. That's the ground rules that you have to follow. If we look at multiplexers, only use multiplexers that are suited for ACIR measurement. Make sure that you check that before you start using multiplexers in the production line. And basically then the same things are applicable as for the regular wiring. Make sure that you twist the source and twist the sense wires and keep wires between the multiplexer and the battery as short as possible. For troubleshooting, the message is always do it one by one. So change one of the possible causes and do a measurement. And step by step find out what the cause of your problem is. For probing, the first and most important thing is use a single contact pin to connect to the battery. It will give you a better reproducibility of your measurement. Avoid metal parts when you build a structure for probing. Sometimes we see that people are using metal parts and metal plates as support for the probing fixture, but then you will introduce eddy current that can have influence on your measurement. And then there is a few general remarks that we want to make. Already consider the testing of the batteries when you start designing the battery production line. If you do it like that, you can create already space for a battery tester nearby the point where you want to measure the battery. And with that, you can reduce the length of your wires. And that's a very important consideration. Another consideration that you have to keep in mind, which is not discussed in the webinar, but what I want to mention anyhow, is that engineers don't like to look into instruction manuals. But in the appendix of the instruction manuals of our instruments, you can find very valuable information. And a lot of the content of this webinar is based on the information that you can find in the appendix of our instruction manuals. So it's worthwhile to look into them once in a while. Okay, then we are at the end of the webinar, and I would like Oliver to start with a Q&A session and see if we have many questions.
Yes, so yes, we're not quite at the end of the webinar. We're really asking your questions. So now it's the time where everybody comes into play. I will not really put myself on there. So there's Roy and also Jutta from our product marketing team who will answer your questions. And thanks for already putting in some. I will start with the first one, referring to page 18, asking whether this is an AC or DC test. Maybe you have also... You could answer this first quickly.
Yeah, 18. There we go. Yes, this is an AC test. The battery tester that is shown is providing an AC signal to the resistor. Yeah.
Okay, then we have a generic or general question from Mr. Auer. How long does it take to measure a battery?
It's in the milliseconds that we can do. So the test itself will take up to 20 milliseconds. So it's a very short time.
Okay. Then I pick up another question from the same gentleman who's asking, what are the main specifications I have to look at when I decide which battery tester I would like to buy?
Of course, it's very important. What is the application of your battery tester? We have basically four standard battery testers, and what you have to look at then is the maximum voltage that you can measure for the battery tester. If you're going to measure a battery cell, then you have a battery tester which can go up to, for instance, 60 volts. But we also have battery testers that go up to 1000 volts for high voltage packs in EVs. So that's one of the considerations that you have to keep in mind. And that's the main one. And the other one is, of course, what kind of resistance value and what is the accuracy of the measurement, because that's also, of course, a very important parameter. Yuta, do you have anything that you want to add to that?
Yes. So basically, the first we would like to recommend for the check with your expectation of the battery voltage, and then second one is what is your expectation of the frequency. So basically, we provide our battery tester. So basically the 1 kilohertz one. And if you wanted to measure it for multiple frequency, so we'd like to recommend for the BT4560, which can operate the multiple frequency.
Yes, so if we want to have, I think, more detailed information, we can follow up after the webinar.
Yeah.
Next question I would like to pick up: how to avoid the increase of internal resistance of batteries during charge and discharge. Is that?
During the measurement with an AC-IR measuring, or because basically when you use an AC signal, you don't charge or discharge the battery, because the current is flowing in both directions, and therefore it doesn't have an influence on the state of charge of the battery. If that's what is meant, or if it's referring to aging of the battery. When a battery ages, the internal resistance will increase. So also the battery testers are used to check the internal resistance of batteries. So for instance, if you want to do tests for second life, also the battery tester can be a useful instrument, because you can compare the internal resistance at the initial, when the battery was new, with the internal resistance when it has been used for a few years, and check if it's still valid to use that one for a second life application.
Okay. Yes, I think we can follow up in depth after the webinar also. We will send out the answers. I have one more question. You're mainly addressing the measurement of internal resistance of the battery here in this presentation, right? So what other measurements have to be performed with batteries, and what kind of batteries does this apply to? Maybe this is a very broad question.
Yeah.
Difficult to answer.
Yeah, there are many different measurements that need to be performed on batteries as well. If you are in the cell production, you also have to check the insulator between the different electrodes before you fill the battery, and after battery has been assembled and filled. Also, you need to do a safety check. So an insulation check basically of the cell to check if it's safe. So there are many more tests that need to be performed, but we focused on AC-IR because we see that we get most of the questions for AC-IR measurement.
Okay. Thanks for that. We have two more questions here I start with a, let's say, more compact one. How strong is the influence of humidity on the measurement result? And how can I calculate this in advance? Do we have anything to...
Is there something that you can reply on that, Yuta?
Sorry, the humidity influence?
Yes.
Yes. So basically, we have a set to the specification of the battery testers, and then if you keep in this humidity level, so the accuracy is how to say the follow for our specification. The out of the humidity level of our specification, we haven't give some specific answer, because it depending on the situation. So basically, please have to keep within our specification, and so that's my recommendation.
Yeah.
Okay. Yes, maybe we can elaborate a bit this in writing. Lastly, I have a question which is a bit long. Maybe you can also read along this from Mr. 𝗄𝗲𝗯𝘀𝗶𝘁𝗲. How can we recognize a situation that the currents are different due to a malfunction in our system? So the electronic magnetic fields do not eliminate each other as the result of a false measurement. Probably. Is that something we can answer on the spot, or would we rather?
I think that we have to look into that and come back to you in writing.
Yes. Oh, yes.
Yeah.
Okay, so that one, I think, so we will actually, there was also one question, if we provide a recording of the webinar, which we do, so we share a link to the recording of the webinar, and we will also in that pick up all the questions that have been asked and send you the answers or replies to the questions that we had. Okay. I have one more thing. Where is that thing after? Okay. So that would be it from the questions that I find here.
Yeah.
There's one more?
One more, but not.
Yes, okay. Okay. So we refer to the twisting the cables. Should shielded wires not be twisted? Do you recommend shielded wires?
No, because it doesn't have any additional impact, because the shielding already should prevent the occurrence of magnetic flux or the interference on the wire. So it's not necessary to twist coaxial cables.
Okay. And then the recording of the webinar, yes. I have a question from Mr. 𝗄𝗲𝗯𝘀𝗶𝘁𝗲 from Mans. Is the difference between crown pins and pointy pins?
Yeah.
Can this affect the cell measurement?
Yes, it can.
Results?
It can, because when you have a multi-point contact, the measurement current is dividing into different, basically different circuits, very close circuits, and multi-point probes also can have irregular contacts, and therefore it's having a poor reproducibility of the measurement. So anyhow, if you do measurements in a production line for batteries, the internal resistance measurement, use a single. You want to say something, Jutta?
No.
Oh, okay. I thought.
No.
Yeah. So no, it has an impact on the reproducibility of your measurement, definitely.
Yes. Okay. And there's one, maybe the last question, because we're going really through 11 o'clock, and I think all the other questions to participants will be answered by email. So that ACIR against EIS method, pro-cons. Can I select ACIR? Can you comment briefly? It's probably briefly.
Yeah, ACIR has the advantage that it's very quick. DCIR, you do charge, discharge. It will take longer time. Depending on how you do the ACI or the DCIR, you're also going to degrade the battery because you do a charge and discharge cycle basically of the battery, and that has an influence. So ACIR has many advantages. The only thing is that you have to install it and use it properly in the production line because it's sensitive for interference. Basically, and that's what we have discussed in the webinar.
Okay, so we do actually have 3-4 more questions. There's actually more questions also coming in. However, it's already 11 o'clock. We are an hour here. Very, very happy to see that a lot of interest in this topic. Mm-hmm. But I think we are exploiting our time too much, and we would like to come back to you and answer that by email. Send it all the answers to your questions, as well as with our contact. We have our contact details here, and you will also get it in the mailing in the follow-up after the webinar. So please contact us with any questions about our products or about technical aspects that you are missing and want to have clarified in more detail. Right, so here you see our email contacts. We will also send it to you. And with this, I would like to maybe bring this webinar to an end. Thank you very much for your participation. For the many of you, thank you very much, Roy and Jutta. And yes, we will follow up soon with the recording and the materials, and hope to see you soon. Thank you very much.
Thank you.
Thank you.
Thank you. Bye-bye.